We have seen in previous videos that when you forward bias a PN junction, it conducts, and when you reverse bias it, it doesn't conduct. In this video, we'll see how to summarize this entire behavior of a PN junction in a single picture. This picture should tell us how the current through the PN junction changes as we change the voltage across it. So the picture we're going to draw is going to be a graph of voltage versus current. So the voltage across the device will be plotted along the horizontal, and the current that flows through it will be along the vertical. All right, let's begin. Let's start with the forward biasing. Well, in forward bias, we've already seen that the positive is connected to the p-type and the negative is connected to the n-type, and a current flows, it conducts, a current flows from p to n. The direction of the current is from p to n. So what does the graph look like? Well, initially when the voltage is very tiny, the current is not very significant. You may recall that there's this depletion region that exists over here, and as a result, there is only a small amount of charges that are about to flow through. It acts like a barrier. But then as the voltage increases, that depletion region becomes smaller and smaller, and as a result, the current is growing. I hope you can see that. And eventually, after a particular point, the depletion region vanishes and the current skyrockets. So this is how the PN junction behaves in the forward bias. And this point, after which the current increases very quickly, we usually call that as the cut-in voltage. So let me just draw that over here. So this point, approximately this voltage over here, we call that as the cut-in voltage. This voltage is called the cut-in voltage. It's also called as the knee voltage or whatever, but usually you can call it as the cut-in voltage. And that for silicon diode is approximately 0.7 volt. This is about 0.7 volt. And so you can see before 0.7 volt, the current is slowly increasing. But once you hit 0.7, then even for tiny changes in the voltage, the current skyrockets. The current changes very dramatically. So that's forward bias. Now, let's look at what happens in a reverse bias. You may recall that reverse bias is when we connect the positive to the n-type and the negative to the p-type. We'll plot this voltage along the negative axis, and in this case is a very, very tiny current that flows in the opposite direction from n to p. A very tiny current. So we'll plot that current along the negative current axis. So what does this graph look like? Well, in this graph, we've seen that that current is very tiny, so pretty much it remains near zero itself. So current is remaining near zero itself. But more importantly, the current is almost a constant. It's almost a constant. We've seen that in the previous videos. And so the graph that you get is something like this. And if you're an electronic engineer, you would absolutely love this graph, because without getting into the details of how and what and why, it pretty nicely summarizes what this PN junction does under various circumstances. It tells us that when you have forward bias it, the current is very low until 0.7 volt, then very quickly skyrockets, and it becomes extremely sensitive to voltage after this point. Under reverse bias, it hardly conducts, it acts like an insulator, but a very tiny current flows through it, pretty much a constant. It's also telling you that this is not a straight line, and as a result, this is a non-ohmic device. You might recall that if you have a conductor, then the VI graph for that would be a straight line. And so it's an Ohm's law works for that. But over here, Ohm's law doesn't work. So it's also telling us that a PN junction is a non-ohmic device. Ohm's law doesn't work. Okay, that's pretty much it. But now let's look at some technical names of this. An engineer would call this as a characteristics. It's called this as the VI, this graph is called as VI characteristics of a PN junction. All right, now even though this is a non-ohmic device, so Ohm's law doesn't really work over here, we like to think in terms of resistances. And so if you go in the forward bias, this is the forward bias over here, notice because it conducts very nicely, we could say it is having low resistance. So we usually say that in forward bias, PN junction has low resistance. Low resistance. And similarly, if you go to now reverse bias, because it hardly conducts, it's acting like an insulator, we would say it has a very high resistance to current. So we would say high resistance. High resistance in reverse bias. And one last thing is, if you were to, draw a circuit with a PN junction in it, it would be tedious to keep drawing this diagram over and over again. So we have to come up with a circuit symbol, right? So here's a circuit symbol of a PN junction. The symbol looks like this. So whenever you are seeing a PN junction used in a circuit, you would probably see something like this. So this side represents the P side, and this side represents the N side. Now notice what the symbol is telling us. The circuit symbol is telling us in what direction our PN junction conducts. The arrow mark is telling us that the PN junction conducts along P to N, from P to N. So if you want this thing to conduct, you better put a positive here and a negative here, forward bias it. On the other hand, if you try to make it conduct from N to P, it won't work. See, there's a barrier over here. It doesn't work. So that's the motivation behind this symbol. And one last thing is that people usually call this PN junction as PN diode, or semiconductor diode, or a junction diode. And the word diode has two things in it. It has the word die, di. Die means two, and that's referring to the two terminals that we have. One side is P and one side is N, the two terminals. And the word ord, well, I really don't know what this means, because there are a couple of sources, which one source tells us that it is a short form of the word electrode, because we use electrodes here. Another one is telling us that it's path. Whichever it is, I don't know what it really is. It could be a short form of electrode or path. But what it's trying to tell us, the word diode is telling us that this is a device in which you can create a path from one electrode or one terminal to the other terminal for charges to flow. You can have a path from P to N under circumstances like the forward bias. But if you reverse bias it, it doesn't allow that. That path is not there. So usually when you hear the word diode, what usually comes to my mind is it's a device which conducts only in one direction. That's it.